Okay, year 12. So we're moving now into the angle between two lines and having a look at how we calculate that. Now, the first point to make here is that the angle between two lines is always acute, unlike the angle between two vectors. So if I've just got two lines, then I'm not interested in the obtuse angle. So here I've got two lines that intersect. This is my angle here that I am going to find. That's what I'm interested in. So when I come to calculate that angle, I'm going to use my dot product formula, which is, I'm going to use, right, that cos theta, if you remember, is equal to the dot product of u and v, if these are my vectors, over the magnitude of u by the magnitude of v. All right, now this is the angle between vectors, right, between two vectors, and this can be negative, and the angle between two vectors can be obtuse. All right, so this is the formula we use for angle between two vectors. All right, because if we're going between two vectors, all right, I'll just do a little example here. Then if this is my u and this is my v, all right, then that here, that's my theta there, because the definition here is the angle between two vectors going in the same direction, if you like. So as they go out in their directions, it's the angle between those two vectors. But if I change the direction of one of these vectors, so let's take v, and v can now be heading out. All right, let's say v is going this way. All right, so that means that this is my v, and v is going out that way now. So the angle between my two vectors is this one here, and that's obtuse. So this can take a value between, this is my angle between two vectors, and theta can go anywhere from 0 to 180 degrees. Okay, so that's the angle between two vectors. But if we're only considering the lines now, we're not considering the direction, then now the angle between the two lines can only be acute, in which case we are going to adjust our formula to make sure that my result here is always positive. So for cos theta equals, yes, u dot v for my vectors uv, but I'm now not interested, I'm not worried about the direction, it's just the acute angle between the two lines that I'm interested in. Then what we'll do is we'll take the absolute value of this, and this is my angle between two lines, and the two lines are still vector defined. All right, now in this case I can only go from 0 to 90 degrees. 0 degrees to 90 degrees. Okay, so that is my setup. So in my diagram here, we probably should just be, this is my angle between lines, and this here, this is my angle between the vectors. In this case, with my vectors going in the direction that they've been labeled there. All right, let's look at an example. Okay, let's find the angle between these two lines. I've got two lines here defined by 1 and by 2. Okay, so the first thing we need to do is to rewrite these equations so that I can see what direction they're heading in. So I'll rewrite equation 1 here. This is equation 1, this is equation 2. All right, I'll write 1 as x minus 2 over 3. That all looks good, but I want to read all of them in the same fashion. So y becomes y minus 0 on 1, and 1 minus z, that's no use to me. I want it as z minus 1, but what I've done is I'm multiplying numerator and denominator by -1 over -1. So that's my equation 1, and what I can see from that, now, that I couldn't see before is that I've got a direction vector that comes to me that falls out of my denominators. Direction vector is 3, 1, negative 1. Okay, so my second equation, see if you can do this now by pausing the video. I get x minus 0 over 1 equals, now 2y is no use to me, so I'm going to write that as y minus 0 over 1/2. Just check that that works. 2y over 1, yep, same deal. And that's equal to z minus 3 over 1. So my direction vector that falls out of my denominator here, my direction vector here will be equal to 1, 1/2, 1. Okay, so I could write that. That's just simplified. I could double each of my terms to make it 2, 1, 2. That's going to make it easier for me to work my dot product and my distances. And so now I get the I'm going to get my theta from the dot product of my vectors. So dot product comes from 3, 1, negative 1, dotted with 2, 1, 2. Now obviously I'm getting a different value because I changed my 1/2 1 to 2, 1, 2, but I'm also going to get a different magnitude, and the same value of my fraction is going to come from that. So I'm over the magnitude now of 3, 1, negative 1, which is 9, 10, 11, by 2, 1, 4, 5, 4, 5, 9. Okay, so this comes to 3, so I get 6 plus 1 is 7, minus 2 is 5, over the square root of 99. So therefore theta is going to be equal to arc cos, I should write, arc cos 5 over root 99. Now we're in, we can answer in degrees or radians, whatever we like. So I go to my calculator and find arc cos. It was 5 over the square root, control root 99, enter. So we get to 3 significant figures, 59.8 degrees. 59.8 degrees. So that's my angle between my two lines as defined by those vectors. Okay, let's do one more example. All right, so this example, we're just presented with some different information. What we need to extract are the direction vectors, and there are many different forms. Now we've got a vector. In the previous example, we had Cartesian coordinates in 3D, so Cartesian equations for 3-dimensional space. And now we're in 2 dimensions. We've got a vector equation and we've got a Cartesian equation. So I guess it's the same. Up here we had we had 2 Cartesians across a 3D space. So same deal though. In example 1, what did we want? We wanted the direction vectors. So we found those and we used those to as our vectors UV. So we dotted them and divided by the product of the magnitudes. So we can do the same here. And if you can work it out, I'd strongly encourage you to press pause and find this angle, and then that's great feedback for you in terms of how you've gone. Okay, so my direction vectors. Direction vector. Direction vector 4. All right, I'm going to call this equation 1. And this is my equation 2. So the direction vector for 1 Well, that's given here, isn't it? That's 2, 3. So nothing to do there. Just to note it, and then my direction vector for equation 2. Okay, well that's given to me by my gradient, isn't it? This is a 2D representation of a line, y equals mx plus c. So my gradient's 2. So my direction vector, carefully now, is rise over run. It's upside down, isn't it? So 1, 2. If we go across 1 and up 2, then I will have a gradient of 2. So they're my direction vectors. So therefore, my cos theta is the dot product of 2, 3 and 1, 2. So we can probably work that out on the fly. 2 plus 6, so I get 8. Now I know, because that's positive, I know I'm getting the acute, but I need to be mindful that I'm taking the absolute value. Over the square root of 4 and 9 is 13 times 1 and 4 is 5. So that's equal to 8 over the square root of 65, which is positive, so I can drop the square root, the absolute value signs. Did I do that here? Okay, I didn't. So that should have been, in the first example, big absolute value signs. We can't have negatives here. 8 over the square root of 65. I now need the angle for that. So in we go to the calculator. And I could just copy that one down, change my 5 to an 8, and my root 99 to a 65. And hit enter, and I get 7.13 degrees. Come out of there. So that's 7.13 degrees, and that's 3 significant figures. Okay, excellent. Exercise 11N is your practice questions. Cheers.